Hello everyone, Namaste. I am Ramnath who would like to share with you the VLSI topic, why EM in soft design an issue to be solved. This is part 1. I will be providing more parts on this one in the coming days. Thank you, and please feel free to share any comments or suggestions. Thank you. Before we understand the EM and its impact, we will first figure out where and when it will occur. Okay, in this soft design of different abstractions, if you observe closely, you will figure out that there is a logic in the small portion, and there is one driver gate feeding another sync gate. There will be a lot of logic nearby, and if you see further, there is this logic is the one which we need to analyze to see where the EM occurs. So this driver, they can be a buffer or an inverter or any other logic gate, and that is feeding another gate. This also can be any gate. So now this conductor connecting to that can go through an impact due to electric field and thermal. So we will figure out the different situations, and we will study this in more detail. Let us analyze the situation as mentioned in example 1, where the gate device under test is a buffer gate for simplicity, and there is a load, and then there is a sync cell. Here the input signal which is having a good transition. If you see there that output of this DUT, if you see that it has almost preserved the signal levels. So this is good enough, and then the succeeding cells will also see reasonably good slew even at the next levels. Here, if you observe, to understand this scenario, the cell will be characterized, the standard cell, and then this will be analyzed in the static timing analysis or in the physical design. So in the EDA view corresponding to that will be a Liberty file. In the Liberty file, if you analyze carefully, there will be timing view of it. Here the output pin and the related pin is the input one. Based on this, the delay information and the output slew information will be mentioned. Here the corresponding input parameters are, in the index 1, the slew value is mentioned at the input. Here different slew will be mentioned like this: sharp slew and bad slew, maximum slew I mean. And similarly the index 2, the load seen by this DUT will be mentioned. So different values. This is the maximum value. So similarly the output slew will be mentioned here. So assume that in a scenario where the slew is so and so, and the output load as seen by DUT is 0.0221. So if you see, the corresponding output slew value will be by this table we can figure out. Since this value at the input is 1, 2, 3, 1, 2, 3, and here the load is second value. So this is the value of the output slew. But if you see here, assume that in another case where the signal strength is same DUT, but here the load is changed. So here again the lumped value is shown, but actually this can be distributed load. However, for analysis purpose, the situation doesn't change. So if you see here, if the load value increases, the slew got degraded. Even the slew here was very good, but once it came to the input of the sync cell, the slew got heavily degraded. Because of this, succeeding cells also get affected. because their slow also will be get affected, their delays will be get affected, and other situations also will come into play. That means like it is prone to crosstalk and other things, and even for higher power dissipation. So to handle this situation, this is an undesirable one in the as per the static timing analysis or as per the physical design. They since this is a bad slow, what is done is like we will again consider the liberty file wherein the slew is same as before, but the load has increased. That means like this is the load table. This is the maximum value to which this cell has been characterized, but if you observe, this has crossed this limit. Okay, this 2.23 is way higher than the 0.91. So because of this, the output slew seen at this point is also very high. That means like it has also crossed this line. That means like 1 2 3 here, 1 2 3 here, but the slew here is way higher. So since this is high, what happens is like in the succeeding stages also of the sync cell, it will be going higher, and the delay computed will also be bad in the case of the sync cell. So to avoid this one, what is done is like this buffer strength can be increased. Okay, so when you increase the buffer strength, assume that theoretically like you have increased the buffer strength, then what happens is we will study the next situation where in this case also the input slew is same as before, but since we have used a different buffer which can handle this larger load, then you will understand that the resulting slew will be coming out to be smaller, and which fits within this earlier table. Okay, of course characterization has to be done up to this maximum value, and you will observe that the resulting slew will be smaller. So since the value is smaller, then the sync cell will react properly, and the next slides also stages also will behave as expected. Okay, but then we have to understand where the main issue is coming. The main issue then will be the EM risk. The reason is like definitely we have handled and kept the transition within the limits. That means like at the input of the sync cell, we have kept the transition within the limits. That means like more or less same as this one. Okay, but if you observe, that is not it. Okay, the load has increased tremendously, and hence we have increased the buffer strength. Okay, drive strength of this buffer. So this one is leading to EM risk. So we need to prevent it by controlling the load value. That is why we have to ensure that transition should be kept in limits and the load also should be kept in limits. That is the main thing. Before understanding how the EM risk uh, will affect the design, we will figure out what it is. Okay, so if you see, this is a metallic conductor, and this is anode and cathode, and assume that this is controlled by a battery. Okay, so here there is one electric field going from anode to cathode, and there is a battery here, assume. Okay, now when the electric field is within the reasonable limits, then you will see the electron flow will be in a specified manner. But now if you observe that the electric field has increased. Okay, so when the electric field has increased, there are so many electrons coming and pushing and going forward. Okay, so if you observe that there are two forces acting here. One force is due to the electric field, which is pushing these ions slightly in the towards the cathode, and also there are some electrons which are having enough velocity. Because of their movement, they are also pushing the ions, but they are pushing because the electrons are moving towards the anode. So the electrons, because of their momentum, they are pushing these ions towards the So electric field is pushing the ions towards cathode and the electrons are pushing the ions towards the anode. So if you observe, actually the electron momentum force is way higher than the electric field force. Okay, so because of that you will observe that the ions will slightly move. Okay, just figuratively it is shown. So you will understand that to know why electromigration is not occurring, the electron movement will not push the metallic ions further towards the anode. We will dig a bit into it. So as we know, the conductors are usually made with metal in ICs. So if you see, metallic atoms have loose electrons in the outer shells, which form a sea of delocalized or free negative charge. Since the outer electrons are shared by all the surrounding atoms, it results in positive ions, which surrounds sea of outermost electrons. If you see, most of the metals have either FCC structure or BCC structure or HCP. So FCC stands for face center cubic structure, as we know, and BCC stands for body center cubic structure. So if you observe, aluminum and copper both are FCC structure. We will try to learn more about that. So this is the usual FCC structure, where in this cube you will observe that all the corners are the aluminum atoms. In the same way here, 1, 2, 3, 4 are also aluminum atoms, and even the middle atoms are also aluminum atoms. So in the same way, top and bottom. So you will observe that this is the picture representation, but note that this is just a visual representation. Okay, there is a lot of open space, and actually if you observe, this is how the actual atoms are placed in the metal. This is called hard sphere model. And if you observe here, there is a cube here again. Okay, and this is the diagonal, and the atoms are just touching each other. Okay, so if you find the diagonal distance, you will observe that this is 1 r of the atom, and this is 2 r of the atom. This is the 1 r. So this is A equal to 4r. This total diagonal equal to 4r, and this length segments of the triangle is A and A. So this is a right angle triangle. So A equal to 2 into root 2r. Okay, so you will observe that in the hard sphere model of this FCC structure, okay, the atomic packaging factor is APF, which is close to 74%. And what it means is like there is 26% void excess. That means like even though the atoms are so packed, there is still some empty space. That empty space is close to 26%. Aside to that, we also know that in the earlier century, the Rutherford gold foil experiment, it was known that there is a lot of empty space within the atom, because the nucleus, which contains proton and neutrons, was densely packed at the center, and there is a lot of empty space. That is why the electrons were beam was going through the gold foil. So based on these two facts, it is clear that the current density through the conductor, when it is below the permitted levels, the electrons under the influence of the electric field drift through the conductor with a few collisions with the metal ions. So that is why they don't displace the metal ions when the EM current density limit is not violated, because there is lot of empty space. Yeah, we will get to know more details on the electromigration. Electromigration is the transport of material caused by the gradual movement of the ions. So where it will occur? It will occur in a conductor where the electron movement occurs. And why it occurs? It occurs due to the momentum transfer between conducting electrons and the diffusing metal atoms. When it occurs, it happens usually at high current densities of that conductor when the EM current limits are violated. So if you observe that, definitely it is understood that electromigration is a serious threat to the long life of ICs. So in the worst case, it leads to the eventual loss of one or more connections and intermittent failure of the entire circuit. So we need to avoid these reliability failures. So since the reliability of interconnects is not only of great interest in the field of space travel and for military purposes, but also with civilian applications like, for example, the anti-lock braking system of cars. So this is how after the conductor suffers the EM, the ions will move towards the anode. So this is the anode, this is the cathode. They will be moving towards it. So figuratively it is shown. Yeah, in this slide we will observe the natural events which occur around us to know more details on the EM aspects. So you will find here that water is going smoothly and it also appears to be pure. Thus, soil erosion is not happening as part of the water current. As we know, EM is analogous to erosion of soil. So this resembles to the current density in a conductor where it satisfies the condition that actual current density is far less than the current density limit of that conductor. Hence, no transport of material happens in the conductor as EM is not occurring. In this case, soil erosion is not happening as evident from the pure water in the river. Yeah, in this case where the water is moving turbulently and a lot of soil also moving along with the water, you can see that the water color is brownish. That means like there is lot of soil in this water. So this resembles to a case where the current density in a conductor is far higher than the current density limit of that conductor. Just like how erosion of soil is occurring as part of the water current, even in the analogous conductor case, the transport of material is taking place due to the EM occurrence. So, like soil erosion is bad for environment, even electromigration is a serious reliability threat to the ICs and it should be avoided. Yeah, I have referred to these articles before I make the presentation, and there is a lot of information on this subject way back in 1969 onwards. So there is a very good amount of knowledge even coming even nowadays. So thanks to so many contributors along the way. I really appreciate the time well spent. Okay, and thank you very much, and have a nice day. Bye.